All right, I had a question about the lab density of water table. This table is very confusing to read.
Yeah.
So this table, what happens is, let's start off at 0 degrees, 0.0 degrees. If we start off at 0.0 degrees, the density of water is 0.99878. And then if we go from 0.0 and we go up to 0.1, did the density just skyrocket? No. The density actually changed so little. How little did it change? Only the last digit changed. And so we went from 999,878 to 999,874.
So those are the last three decimal places.
Yeah. And so what they wanted to do is they wanted to avoid having to write those digits over and over again. And so this one would be 999,881, 999,887, etc. Now, there's a problem here, and let's see. The problem happens when we hit this. Now we go from, we're doing the 999s, and eventually we're going to get to 999,999. So it's going to be 0.999999. Well, what's going to happen? Well, it's going to go up. It's going to go up too. And so, do you see this asterisk?
Yeah.
This asterisk means the first three digits have now changed to the next series of first three digits. So, all the way up to here, we use the previous three digits, which is 999. Now we have to use the next series, and the next series of three digits is actually more than three digits. It's 1.000. And so once we hit that asterisk there, then it's 1.0000000. So that's 6 zeros. Does that make sense?
Yeah, no, that's
A lot of people will say, okay, what is the density of water at, what is the density of water at 18.3 degrees C? A lot of people say 588 grams. Well, that would make it so much more dense than gold. You know, gold's only 20 grams. So nothing's that high unless you're dealing with subatomic particles. Then it's much higher. All right, any other questions?
Professor, that TY, the total yield.
TY is called what again? TY is not total yield.
Oh, you're right.
Yeah. The theoretical yield is how much you expect to form based on your limiting reactant, but you don't always get that amount. And so let's say you needed 100 cookies for an event, but you always end up eating some of them, right? And so you have to compensate for that because your yield, isn't going to be, if you plan to bake 100 cookies, your yield isn't going to be 100 cookies for the event, it's going to be less. And so maybe you should bake 105 cookies to compensate for the loss, right? And so if you kind of have an idea of how many you're going to end up eating, then we can compensate for it. And so a lot of these reactions, they give a fairly consistent percent yield. And we can compensate for that. And so here in this particular reaction, we have solid sodium nitrate decomposing. And this reaction, under one set of conditions, gives a consistent yield of about 95%. So if we're going to lose about 5% of it, we can compensate for that. So this is the next example calculation. Let's go ahead and compensate for this here. Based on a 5% loss. You know, not that it's going to be 95. You know, the percent yield varies from experiment to experiment. And so we're just estimating this so we make sure we have enough. Or we make sure we know how much we're going to form. This is making sure we know how much is going to form. And so solid sodium nitrate, what's the formula for sodium nitrate? Okay, that's solid. Decomposes into sodium nitrite. What's the formula for sodium nitrite? Yeah, good. And oxygen gas, O2 gas. All right, this is an example of what type of decomposition. Is it a metathesis, acid base, or redox decomposition? This one turns out to be a redox decomposition. Over here, we have elemental oxygen. It's going into a compound over here, so it's -2 over here, but it's 0 over there. So there's a change in oxidation states. The change in oxidation states will give you a clue, because acid base and metathesis, the oxidation states don't change. The oxidation states are fixed. So, this is also different. Normally we would do a skeleton redox. You know, we mix it, see what happens. So this, we try to heat it up, it's decompose it, this is what happens. However, we don't have to do skeleton redox here because they're telling us all the ingredients that are present. So sodium nitrate, we just need to balance it. So how can I balance it? We have one sodium, one nitrogen, 3 oxygens. Here we have 4 oxygens. How can I get? Well, if I take 2 plus 1 would do it, so I'll just take 1/2 a mole of O2 here. Is it okay to have fractions? It is actually okay to have fractions. I could do that, but in stoichiometry, having fractions is a hassle. So the easiest thing is just to double it. Get rid of that fraction. This would be it. So I'd end up with 6 oxygens. That's 4 plus 2 is 6 oxygens. Good. Here, since there's only one ingredient, we don't have to worry about limiting reactant, excess reactant. There's only one reactant. And that one reactant is 1.5 grams of sodium nitrate. So we're starting off with 1.50 grams of sodium nitrate. And what we want is how many grams of sodium nitrite will be produced, assuming that we have a loss of about 5%. And so how should we solve this? We're going to go from grams of sodium nitrate to moles. So sodium is 22.99. Nitrogen is 14.01. 3 oxygens is going to be 48.00. It's 10, 10, 15, 8, 5. And so a mole of sodium nitrate, formula units, weighs 85.00 grams. The grams of sodium nitrate cancel. Now we have moles, so we want to go from moles of sodium nitrate to moles of what? Sodium nitrite. There's a 2-to-2 mole ratio, so 2 moles of sodium nitrite for every 2 moles of sodium nitrate. A 2-to-2 or 1-to-1. We can simplify it. 2 divided by 2 is 1. And then we want the mass of sodium nitrate, so we want the grams. So sodium, 2299. Nitrogen is 1401. And 2 oxygens will be 32.00. We're going to get 69.00 grams of sodium nitrite per mole of sodium nitrite 4 millunits. So everything cancels out, and leaving us with grams. However, I don't stop here, because if I stopped here, do you know what we call this? We call this the theoretical yield. There's only one reagent, so that reagent's got to be the limiting reagent, right? There's no excess reagent in this case. And so the yield based on the limiting reagent is called the theoretical yield. But they don't want the theoretical yield, they want the actual yield. And so how can I get the actual yield? Well, that comes from for every 95 grams of actual yield, they had to have 100 grams of theoretical yield. That's a 95% yield? Yeah. And so this is our 95% yield. For every 95 grams of actual, we had to, in theory, make 100. And so this is like if you eat 5 cookies for every 100, then you plan on making 100, then you're only going to end up with 95, actually. And so let's see what that turns out to be here. So 1.5 divided by 85 times 69. So in theory, I should make 1.217 grams. In theory, I should make 1.217 grams. I have enough ingredients to make 1.217 grams. But unfortunately, due to some circumstance, I'm going to lose 5% of that. And I'm only going to end up with 95% of that. And so, in actuality, I'm going to not end up with 1.21, I'm going to end up with 1.156 grams of sodium nitrite, because I'm only going to get a 95% yield. I'm going to lose about 5%. Does that make sense? Your book is going to call it actual over ideal. So they have 95 gram actual yield or 100 gram ideal yield or 100 gram theoretical yield. Okay, any questions on this limiting reagent stuff? Skip ahead. And we're going to talk about energy in stoichiometry. So first, energy. Back in chapter 1, we talked about energy. Do you recall the total energy? There's 2 types of energy: the kinetic energy and the potential energy. And then there was some person on the swing. There's a little figure of that. So let's talk about energy in general. Energy, there are different units that we use. The joule, capital J, is the SI unit of energy. SI stands for the International System. And so this is the standard for energy. The way the joule is defined is this. 1 joule is defined as a kilogram meter squared per second squared. Where does a kilogram meter squared per second squared come from? it comes from taking a kilogram. A kilogram is about 2.2 pounds. It's more. It's about 2.2 pounds. So you take a kilogram and you lift it up a meter high. So if this were a kilogram, I lift this up a meter. You know how much energy I just used? In theory? 1 joule. I just used 1 joule of energy to lift that up. In reality, I probably use more than that because the energy conversion into motion like this is not 100% efficient. But the minimum amount of energy required to do that is 1 joule. And that comes from the units here. If we take a kilogram and lift it up by 1 meter, and that takes care of the kilogram here in one of the meters. And then what's left is meters per second squared. Have you ever heard of meters per second squared before? If you take physics, you'll hear meters per second squared because anybody taking physics will memorize 9.8 meters per second or 9.8 meters per second squared. Have you heard it before? Yeah? No? Not yet? Not yet. Not yet. 9.8 meters per second. This gravity. This is what we call gravity. What does G mean? That's 1G is the force of gravity on our G. That's 9.81 meters per second. This is gravity. And so what we're doing is when we're lifting up this mass by 1 meter, we're fighting gravity, right? So we have to use energy to fight gravity. Right? It's SI unit. One of the most common units is the calorie, abbreviated CAL with a lowercase c. The calorie is very simple to define. It's the amount of energy required to heat up 1 gram of water by 1 degree C. So if you have a gram of water, a milliliter of water, it'll take 1 calorie to warm that milliliter of water by 1 degree C. It turns out that's more energy than it is required to lift a kilogram mass. In fact, a calorie is about 4 times bigger than a joule. Therefore, it takes about 4 joules to make 1 calorie. In fact, this is known more precisely. 1 calorie is equivalent to 4.184 joules. This is not exact. I don't know why they're doing definition here. They should do this one definition and this one just the equal sign. They screwed that. And then we have, but a calorie is kind of small. A joule is kind of small. And so we deal with kilojoules most often and kilocalories. And so typically we talk about kilojoules, not joules, but sometimes we talk about joules. Typically talk about kilocalories. Some people don't like kilocalories because kilocalories is 1,000 calories. And so there's something called a food calorie. So let's say you had, you just had a 2,000 calorie meal. If you had a 2,000 calorie meal, how many grams of water can you warm up by degree C? So remember, 1 calorie, we can warm up 1 gram of water by a degree C. So if we have 2,000 calories, we can warm up 2,000 grams of water by degree C. But if we have 2,000 food calories, do you know how much? We can warm up 2 million grams because a food calorie is 1,000 chemical calories. And so to note that distinction, for food calories you use a capital C. For chemical calorie we'll use a lowercase. So 1 food calorie can warm up 1,000 grams of water, not 1 gram of water. 1,000 grams of water is a liter. Water, or 1,000 milliliters. So the first series of problems just deals with unit interconversion. You know? So if I have 42.5 kilojoules, how many kilocalories, how many calories, and how many joules is that? So we could do some unit conversions here. Probably the easiest is to figure out how many joules. So if I have 42.5 kilojoules, how many joules is that? Well, the kilojoules abbreviated K, capital J. And there are 1,000 joules in every kilojoule. And so I'll have 42,500 joules. Okay, to make sure the sig figs are right, you might do it in scientific notation. 4.25 times 10 to the 4 joules, or 42.5 times 10 to the third joules. A lot of people like 10 to the third because that's a kilo. 42.5 kilojoules. Okay, then let's go to calories. I think that would be the easiest one to do next. We could do a separate calculation. 42.5 kilojoules. And what I would do here is I'd go from kilojoules to joules. So kilojoules to joules, there would be 1,000 joules per kilojoule. Those just cancel. And then we have this conversion, the relationship between joules and calories. In 1 calorie, there's 4.184 joules. So joules cancel, that leaves you with calories. So how many calories is that? So 42.5 times 1,000 divided by 4.184. 10,157.7. To the correct number of sig figs, we're allowed 3. And so this would be 10,200 calories, or 10.2 times 10 to the third calories, or 1.02 times 10 to the fourth calories. Either way. A lot of people like it 10 to the third because you know what 10 to the third is? A kilo. So it would be 10.2 kilocalories. We could see that if we would just redo the problem. 42.5 kilojoules. We'd go from kilojoules to joules, 1,000 joules in a kilojoule. And then joules to calories. 1 calorie contains 4.184 joules. And then calories to kilocalories. 1 kilocalorie, or kcal, is 1,000 calories. That gives us 10.2 kilocalories. Now your book does this. Do you see what your book did? they have all these ones where they do this. Remember millimoles? Well, they're doing the same thing. They do 1 millicalorie is equal to 4.184 millijoules. Kilo and whatever else. I don't like to do that. I just like to have the same one. That way I always remember it. And then just go. It's like the heart of the stoichiometry map. The heart of the stoichiometry map is a mole-to-mole conversion. So for me, it's not a millimole to millimole conversion or a kilomole to kilomole conversion. I don't like those myself, but it's just personal preference. You can do it whatever way you want. Even though I don't like it, I don't care if you use it or not. And so, anyway, I would always go to the same. It's okay. All right, so those are some unit conversions. And then we have energy and chemical reactions. So let's take a look at thermochemical equations for the chemical reactions. You know, so combustion reactions, oftentimes a lot of heat's involved. Like if we burn methane, you know, one of the purposes of burning it is to get energy. And energy can be as heat given off or absorbed, and a chemical reaction can be measured in the laboratory. So the change is called heat of reaction. So if we burn some methane, there's going to be heat associated with that reaction called the heat of reaction or enthalpy of reaction. Enthalpy is a very strictly defined term, and there are some restrictions on enthalpy, which we aren't going to talk about in this class. And so a lot of people, when they think of enthalpy, they just think of the heat of reaction. This is either the heat given off, or some reactions, when heat is given off, we call that reaction exothermic. Exothermic, heat is given off. Some reactions absorb heat, and those are called endothermic. Endothermic absorb heat. But we have this thing called the first law of thermodynamics. The first law of thermodynamics says that energy is neither created nor destroyed. So if energy is given off by a reaction, that energy goes somewhere. Well, that energy is going to go to you. You know, so if you're standing here next to the flame, you're going to get hot because the reaction is giving off energy, and you're absorbing that energy. Or if there's a reaction that absorbs energy, you're going to get cold because that reaction is absorbing heat, you're losing it. And so we have exothermic and endothermic reactions. And so H is the symbol for enthalpy or heat of reaction. And normally if there's a reaction, there's a change, so we use the delta. Delta either means heat or means change. In this case it means change. And so we have delta sub RH. This is the heat of reaction. Now, there's a way of keeping track. If you lose energy, we call it negative. If you gain energy, we call it positive. It's like when you're keeping track of your balance, your bank balance. If you withdraw money, it would be negative, right? If you deposit money, it would be positive. And so if you withdraw $10, that would be negative $10. But is there such thing as a negative $10 bill? No. There's only a positive $10 bill. There's no negative $10 bill. And the same thing happens with energy. There's no such thing as a negative 10 joules. Negative 10 joules just means you lost 10 joules. Negative $10 means you lost positive $10 out of your account. And so we have to keep track of that based on this. And so when I'm looking at this, let's look at the combustion of ethane. This is the heat of combustion of ethane. This is the heat of combustion for 2 moles of ethane. And so we have this. When you burn 2 moles of ethane, 2,855 kilojoules is given off. It's exothermic, so it's being lost. Well, if it's being lost, then the reaction is losing that. We call it minus 2855. But there's no such thing as a minus $28.55 bill. In other words, this negative is just for bookkeeping purposes. And so another way of bookkeeping is like this. This is showing this with this being lost as product, the reaction here. So positive 28.5 kilojoules. So we got to just keep that in mind here. If it's endothermic, then there's no problem. Endothermic here will have a plus 92. This is gaining. And so the plus sign means it's going to be on the reactant side. It's being consumed. The negative sign means it's on the product side. So this would be our thermochemical equation down here. This is our standard chemical equation telling us the heat of reaction. This is our standard chemical equation here telling us the heat of reaction. And what can we do with these numbers? Well, we can do stoichiometry with these numbers because those are just another quantity relationship, another reactant or product in the chemical reaction. And so let's take a look at this problem here. The thermal decomposition of limestone, solid calcium carbonate to lime, solid calcium oxide, gaseous carbon dioxide. So, let's see. Check something really quick here. All right, thermal decomposition of limestone, calcium carbonate. So we have some calcium carbonate here, solid, and we heat that up. So delta can be used as a symbol for heat. Typically when it's written under an arrow like this, we just heat it. Thermal decomposition is just heating it up. Of limestone to solid calcium carbonate, CaCO3, and lime. Lime is CaO, sorry. And gaseous CO2. Lime is a key ingredient in concrete. As an endothermic reaction requiring 178 kilojoules per mole. And so to show it's an endothermic reaction, we write the heat of reaction like this, delta HR is equal to plus 178 kilojoules. The plus tells us that this goes on the reactant side, not on the product side. But let's make sure this is balanced first. Is this balanced? Yeah, this happens to be balanced. And this is kilojoules per mole of calcium carbonate. Per mole of calcium carbonate means, for every mole of calcium carbonate, I'm going to require this much heat. So I put that in the equation like this. 1 mole of calcium carbonate requires 178 kilojoules worth of energy to decompose it into calcium oxide, 1 mole, and carbon dioxide, 1 mole. I have to be careful because energy is extensive. What happens if I have 2 moles? Is 178 kilojoules enough to heat up 2 moles? No, it's only enough to heat up 1 mole. So if I have 2 moles, I need to double this. And so I have to be aware of that. And so we need to write the thermochemical equation in 2 forms. Well, this is form 1. This is form 2. As a reactant. It's endothermic. Exothermic means it's a product. So once we have this, then we can do stoichiometry, because we have the mole ratios here. And so again, this top one, this top one I'm going to ignore because it's particulate. The bottom one we're going to worry about. So I can go from energy straight to moles. So now, the relationship between moles and energy is given by this equation here. These are all moles. This is the energy. And so I can go from energy to moles of A to moles of B, moles of B to energy, or whatever else I want, grams, etc. All right, so let's do this one. One mass of liquid N-octane, C8H18L, a component of gasoline, must be burned to provide 9.05 times 10 to the 4 kilojoules of heat. And then they give us the heat of reaction. The heat of reaction is minus 5471 kilojoules per mole of octane burned. So I have the energy, and so I can go from energy, I can go energy to moles using this, because here's my relationship between moles and energy. But I'm going to write out the equation in two forms, just to get more practice with that. And so one form is octane. Let's go ahead and balance that. C8H18 liquid plus, when we burn it, what do we react it with? Reacted with O2. Yeah, this is going to form carbon dioxide and H2O. All right, so let's go ahead and balance it. I have 8 carbons. I'm going to need 8 carbon dioxide. I have 18 hydrogens. I'll need 9 waters. That'll give me 18 hydrogens. And that's going to give me 16 plus 9. There's 25 oxygens over here. So I have 25 oxygens. Over here I have 2, so it's going to be N times 2 is equal to 25. And so N is equal to 25 halves. So this is 25 halves. Now, do I like fractions? No, I don't like fractions in stoichiometry. And so what we do is we get rid of the fraction. We get rid of the fraction by doing what? Multiplying by 2. And so alternatively, I could go 2 C8H18 liquids plus 25 O2s gives us 8 CO2s plus 9 H2O liquids. Yeah, you're right. I got to do both sides. Not 8. It's going to be how many CO2s? 16 CO2s plus 18 H2Os. Gas, this is gas, this is liquid. So delta HR is equal to minus 5471 kilojoules here. Is it the same here? The heat of reaction here? Well, if I multiply everything by 2, I have to multiply everything by 2. And that includes the energy, because if I burn twice as much, I should get twice as much heat. Okay? And so this is not going, it's going to be 2 times minus 5471 kilojoules. That's it. Because this is 5471 kilojoules per mole, 1 mole. This is going to be 2 times that per 2 moles combusted. Does that make sense? And so this is the reason why some people leave fractions. Some people leave fractions because they don't want to change it. You're given the heat of combustion per mole. And so this negative means it goes on the product side or the reactant side. Is heat released or is heat consumed? negative sign means it's exothermic. Exothermic means it's consumed or produced. Exothermic means it's heat is produced. It's released. And so that means the other form of this equation will be C8H18L plus 25 halves O2 yields 8 CO2 plus 9 H2O plus 5,471 kilojoules. And so these are the two forms of the equation that we have. Now let's do the calculation here. So I want 9.05. 9.05 times 10 to the 4th kilojoules of heat produced. If I want that much heat, then I know here that I'm going to have minus 5471 kilojoules for every mole of ethane or octane, sorry, combusted. And so the kilojoules cancel, so I go from energy to moles, and they want what mass. And so I'm not going to do a mole-to-mole conversion since I already have the right stuff. And so I just need the mass of A. And the mass of A is 8 carbons, so that would be 8 times 1201. 80 plus 16, 9608 plus 18 hydrogens. 18 hydrogens would be 1818. 114.26. I'm going to have 114.26 grams of C8H18 per mole. And so let's do that here. 9.05 times 10 to the 4th divided by 5471 negative times 114.26. And so I get negative 1,890.0 grams. Well, that's inconvenient, so let's go with negative 1.89 kilograms. And so all I need to do is go way out to about negative 1.89 kilograms worth of octane. Is that possible? Is there such thing as negative grams? No, there's no such thing as negative grams. And so the math is a little bit funny here. The math doesn't work out, does it? Because they give us the conversion factor here, which I use. I use it as minus 5471 kilojoules per mole. So I just flipped it. A mole of octane is minus 5471 kilojoules. But it gives me negative kilograms. So there's a problem here. And the problem is what we're going to do. We have to modify this. Something like this. You know, if you withdrew $10 from a bank, and now your balance is minus $10, you don't say, you know, I need to go get a minus $10 bill from the bank, right? You just say I withdrew $10. But if you just say $10, you know, I went to the bank, $10. Well, $10, you don't know if you withdrew it or if you deposited it. And so this is why we have the sign convention. We have the sign convention to keep track. Did you deposit or did you withdraw? If we decide to omit the sign, and we go, hey, there's no such thing. So I'm going to omit this, 1.89 kilograms. There's no such thing as negative grams. This is like negative atoms. This would be negative atoms. And so I have positive, but now I don't know. Did I withdraw it or did I deposit it? And so what we can say is something like this: 1.89 grams, consumed. Or we do this, and so this is the advantage of using an equation like this. An equation like this will always be positive, except on one side it's produced, on the other side it's consumed. And so we would rewrite this equation like this. It would be 9.05 times 10 to the 4th kilojoules. And then this conversion factor says for every mole of C8H18, I have 5,471 kilojoules of energy produced rather than consumed. Okay, and so what I can do is I can get rid of the sign and keep track of it verbally. Okay, I made a withdrawal, I made a deposit, rather than saying negative $10, positive $10. It's easier saying negative $10 withdrawal, positive $10 deposit. But in this case, we'll have to say it verbally. Are we out of time? Yeah. All right, and so this is what we do with the sign. The sign is important because the sign keeps track of things. Do you see what they did? What did they do with the sign? You look here, they got rid of it. But if you get rid of it, then you should say, whether it's produced or consumed. This problem comes up in math and science, and it's called a phase problem. This issue of losing information. Because what's the square root of 4? Square root of 4 is 2 or minus 2? Is it 2 or minus 2? Well, the thing is, we don't know. It could have been 2, because 2 times 2 is 4, or it could have been minus 2, because minus 2 times minus 2 is 4. So which one was it? Was it plus 2 or was it minus 2? Well, we lost that information. We lost that information, and so to keep track of that information, we keep track of which direction it goes into. And so the way we keep track that this was minus is by saying produced. Because if we all of a sudden go to this, we don't know, was that plus or was that minus? Well, if we write this, then we know it was minus originally. Okay. All right, that's since we're out of time, I think that's it. Are we out of time, or do we keep going? All right.